we can start recording. So usually we do it once you start your talk, but we can actually start now just in case we forget. So
Okay.
Yeah, but I think both me and Alex is recording.
Yes, just make me.
Yes, you can. Yeah, Brian, you can also record too. That's maybe your because your audio maybe is even better. So
yeah, it might be. Yeah, my fancy podcast audio. Are you guys mostly in person there, or do you guys have restrictions still?
most of us are not yet back actually because the policy. Yeah.
Uh-huh. I got it.
But the essential experimentalists or observers, I think they're back.
Oh, cool. That's good.
For San Diego, as long as you submit the vaccination proof, then you can return right to the office.
Yeah, that's right. Yeah, exactly. Yeah, we can be here. We've got a bunch of people teaching with masks on. It's I thought last year was surreal. We were outside in huge tents, but now we've got outside with masks on. Unless you're eating. So I invented a new technology, which is called the chewing gum, and drinking in Diet Coke all day long obviates me from wearing my mask. But I've yet to patent that solution. And we usually go for 45 minutes or an hour with questions.
Yeah, 45 minutes and then 15 minutes of question would be good. But
Perfect.
yeah, you can see because maybe there's already will be some. Oh, actually, so when people ask you question, can they interrupt you during the talk, or you?
Oh, sure, yeah.
Okay, cool. Then people can interrupt.
Yeah. Hi, Gordon.
Oh, hey, Brian. Good to see you.
Yeah, I told you I'd make it finally, but
I'm glad we're finally here, even if it's under compromised circumstances.
Yes, that just means you owe me some pizza and some buffalo burgers when I come out to visit someday.
I've got all the chewing gum and Diet Coke you can consume.
Be careful. You don't know how much I can consume. All right, I'll start sharing my slides here. Actually, I'll share my screen.
And we can start in 1 minute. Yeah.
Okay. Yeah, perfect.
File. So I say correctly.
You see it, Yudai?
Yep, that's good. That's
okay, great.
And let me also get you. Yes. Yeah, I got it. Okay, I think we can start. So we're very happy to have Brian, Professor Brian Keating from University of San Diego. And here's so giving us a very exciting talk. So here's the introduction of Brian. So Brian is the Chancellor's Distinguished Professor of Physics at UCSD and the host of the Into the Impossible podcast. He's also the author of more than 200 scientific publications, 2 US patents, and the best-selling memoir that is losing the Nobel Prize. And also, and Brian received his bachelor's degree from Case Western Reserve University in 1993 and his PhD from Brown University in 2000. Later, he was a postdoc fellow at Stanford and Caltech, and in 2007, he received the Presidential Early Career Award for scientists and engineers for inventing the BICEP telescope. Wow. And Keating was elected Fellow of the American Physics Society in 2016 and is principal investigator of the Simons Observatory in Chile. And he's a commercial pilot, oh wow, with multi-engine instrument ratings and is an honorary lifetime member of the National Society of Black Physicists. Yeah, thanks, Brian. Please take over.
Yeah, it's a pleasure to be here or be here, not there. I'd rather be there. The weather today is quite atrocious, if you can believe it, in San Diego. I always say the easiest job in the world is San Diego meteorologist, and the hardest job is San Diego sportscaster. The only team, thanks to your Cubs, to never win a major city, to never win any kind of professional sports championship, especially in baseball. My beloved Padres were eliminated, but they were only eliminated in the last week of the season, which is pretty impressive. Normally they're eliminated, opening day. So it is a pleasure to be here. I did want to talk about something that you may not be as familiar with if you follow CMB, field, experimental, observational, theoretical, of which Fermilab and the Chicagoland area is, of course, a major contributor to and player in. But this is kind of a differential aspect that I want to bring to people's attention in hopes that I can get, brilliant people like you, Dai, and others, my friends Dan and the wonderful folks you have out there, to maybe turn their considerable intellects our way here. And this is to look for violations of fundamental symmetries in the cosmos, not using laboratory or solar system tests, but actually using the longest optical path lengths possible to reveal perhaps violations of the most sacrosanct laws of nature that we hold so dearly. So thanks again, Udai, for inviting me, and Gordon for so many years in the works, and also my friend Dan for being such a good friend of mine and my show. So yeah, please do subscribe. I only have a couple of prices of admission. Luckily, one's free and one's 99 cents. That is my new book, comes out tomorrow. Think Like a Nobel Prize Winner, based on the 9 interviews I did with Nobel laureates, ranging from Sheldon Glashow to Ray Weiss to Barry Barish, who actually wrote the foreword. And if you take a picture of that QR code, it'll whisk you away to Amazon, where you can buy the Kindle version for just a mere 99 cents for 1 week only. And that's because, I already made so much money from my first book that I really don't need. No, I didn't. Nobody writes a popular science book, as Dan can attest, to become a multimillionaire. So I wanted to get this into as many young people in STEM, because it's really a way to turn the lessons, not the knowledge of these Nobel Prize winners. We can learn that from their Nobel citations and what have you, but actually their wisdom, I think, is more valuable. And so this distills them into the soft skills that we often neglect when we're teaching our students, our postdocs, advising people in STEM. And these wonderful laureates provided me a great deal of wisdom, which I hope you'll enjoy. So yes, 99 cents only. Remind you at the end, and some custom illustrations I had made up for the book. I have a new podcast by the same name called Think Like a Nobel Prize Winner. Get that wherever podcasts are sold. That's actually out now. So you can get the whole book for free effectively if you can't afford that 99 cents. I know times are tough, but hopefully you guys will do that favor, because I want to get it into as many people's minds as possible. And then the other one is free, strictly free, and that's the Into the Impossible podcast, my channel on YouTube, where I host these 9 Nobel laureates. I actually have 10 and 11 and 12 queued up coming in the next few months. And we even had your very own Dr. Dan Hooper, who came on this past spring. I've had on many people from Michio Kaku, Neil deGrasse Tyson, all the way to Juan Maldacena, and hoping to get Gerard at Hooft and many more luminaries, as well as folks like Jill Tarter and others. So yeah, please do subscribe, join, hit different bells, not the no bell, but hit the actual bell. There's Dan and me chatting back G-2, which is very exciting. And I salute all those who do outreach to the public, who pay our salaries. After all, any of us who receive government funding, certainly, especially those of us who are professors at public universities. As I said, I'm going to talk very briefly about the headline that most people hear about when they hear about the CMB and its B-mode polarization, which is potential constraints on inflation, of which I will provide a new insight or a new result that's coming soon to the archive and PRL, hopefully in the week or so, and that's from Bicep Array, Bicep and Keck team rather, but I'm going to spend most of my time not talking about B modes, not talking about inflation, something I find particularly startling, interesting, and perhaps revealing of violations that we as physicists hold sacrosanct relative to Noether's theorem and fundamental conservation laws. And if those were to be manifestly violated, there'd be a concomitant breakage in the underpinnings of all of physical law in a way that I think would have a twofold benefit. One, it would provide full employment for theorists for all eternity, but it would also provide a glimpse into perhaps maybe our only glimpse into, so-called physics beyond the standard model in ways that we could test for a quantum theory of gravity. So I think it's really exciting. And then I'm an experimentalist, so I want to talk about my beloved experiment, the Simons Observatory, which I'm privileged to be the foundation's PI of. And we have many, many cool things in store with that observatory coming online in less than 2 years. And I want to talk especially about some of the most pernicious effects that we as physicists deal with, which are primarily in the domain of systematic effects and actually the ability to use drones to solve these vast cosmic puzzles. And again, Udai mentioned it, but please do feel free to raise your hand just so I can see it. And then Udai, if you can alert me if anyone has a question, or you can just unmute, that'd be great. Yep. So who was the first moral relativist? Well, I think the first relativist in history, I don't know if he was a moral relativist. He's certainly a fascinating character. And actually my next book is an audio book, and it's with Carlo Rovelli, Fabiola Giannati, Jim Gates, and Frank Wilczek, and my friend Lucio Piccirillo. And it's the first audiobook ever done for Galileo Galilei's works. And this one's the dialogue, in which he discusses this very scenario, which is shown here, where he's on a boat and he's talking about fishes and what would happen if the boat's being blown and you drop a heavy object, and or you see fish swimming, and or you see flies buzzing about inside the cabin. As the boat moves at some speed, how would they behave? And this is the first instantiation of a concept of relativity, and it comes from the dialogue. And I'm very privileged to announce that book, hopefully audiobook only, the printed book has been out for some 400 years almost, but the Dialogo, most famous book in history, in fact, kind of transcends science itself, as Albert Einstein said in his foreword, it's the most important book ever written. And that I had Frank Wilczek, the honor of having Frank Wilczek read the foreword written by Albert Einstein about Galileo, which is quite astounding. So the concept of relativity is old, and yet we still want to test it. We don't ever take the opinion of authorities. And certainly Galileo was an authority, but of course he was superseded in many ways by Albert Einstein. And Einstein talks a little bit about that in the foreword to that magnificent book. So the question of whether or not the Earth occupies some privileged status, or motion is detectable, absolute position. Are there absolute four vectors? That's the way I like to think about it. Are there absolute four vectors? Are there absolute frames of reference in the universe? And Udai mentioned I went to Case Western, not far from where you guys are, in beautiful Cleveland, Ohio. And we had the honor and the privilege of having that experiment, the Michelson-Morley experiment, who after Galileo's relativistic experiment still didn't take the maestro's word for it, and they decided to test for their movement with respect to the aether. And there's an image of the apparatus, which is not far from where you guys are, in the basement of the physics department at the Shankland Auditorium and so forth at Case Western, where I did my undergraduate. And this experiment was really considered in many ways the most important, quote unquote, failed experiment because it failed to detect this effect. And I like to think of it as, kind of maybe putting a little bit of the giving a little bit of a back reaction, if you will, to Karl Popper and others, who talk about the prospects for experimental testability as the sine qua non of science. And even, I like to point out, even Popper was a huge supporter of the steady state universe, which kind of maintained what was known as the perfect cosmological principle. In other words, the cosmological principle states that the universe is on large scales isotropic and homogeneous. And they said, well, Einstein connected this to a notion of space and time unified together. So really, you shouldn't expect there to be a time translation asymmetry in time either. And therefore, the Big Bang would maximally violate that symmetry. And so they and others, Tommy Gold and others, supported a notion of an eternal universe slowly oscillating and cycling. And these models are actually still in vogue. My friend Paul Steinhardt writing me early this morning about some new discoveries in his preferred model, the bouncing cosmological model. I have a video on my channel about Sir Roger Penrose's conformal cyclic cosmology and how we could falsify that, and what the virtues are of having a model of cosmology that has no singularities within it. And I think those are fascinating to consider. Singularities give cosmologists a lot of grief and may not be physically realizable in our universe. So it pays to kind of consider alternatives. So for many years, we've tested the notion of relativity and not taken it for granted. And the question still remains to this very day, are we totally sure there isn't a preferred four vector in the cosmos, a preferred system, position, for momentum, or for position that indicates a preferred frame? And we aim to test that in ways that I plan to explicate now. Before I do that, it is legally incumbent upon me to describe the progress that we've made in experimental cosmology since the 1960s, when the first serendipitous discovery of the CMB was made in New Jersey, at Holmdel, New Jersey, which formerly known as Bell Laboratories, now known as Nokia. And it's quite a special place to go and visit. It's part of the historic monuments, as I know, believe the Wilson building is there. And it's done so for great purpose, because it was really there that we started to launch one of the most precise and accurate probes of cosmic history. And in doing so, we've learned a great deal about the universe from ground, balloon, and spaceborne instrumentation, including the detection of E-mode polarization, including the claimed detection of B-mode polarization, and actually the actual detection of lensed B-mode polarization, which is where the CMB's E-mode gets gravitationally lensed and warped and twisted into a B-mode polarization. But of course, we all know, some of us more than others, about the retracted or not confirmed, contradicted results of BICEP 2. And I'll talk a little bit about that in just a bit. And that was to detect possibly the quantum fluctuations leading to primordial B-mode polarization. And if that were held up and verified, which it was not, that would have been seen as the strongest possible evidence that one could get, at least at present, for an inflationary cosmogenesis event, an inflation-like event near to the Big Bang itself. And so I think it's fascinating that we're rightfully concerned with making these detections. And as you may know, in the Chicagoland area, the S4 CMB stage 4 experiment is proceeding apace with proposals and white papers in. The decadal survey is hopefully going to be out anytime this moment. It could come out during this talk. And we have expansion plans for the Simons Observatory as well. And these are billion-dollar class experiments in the case of CMB stage 4, $100 million in the case of the Simons Observatory, fully funded. And I think it's fascinating, so much attention, rightfully so, to these origin events in the universe. And we kind of got a glimpse of that early on in cosmology, or 7 years ago this year with the BICEP 2 event, which I'll harken back to in a bit. But if you had microwave eyes, this is what you'd see over the Simons array, which is now operating in the Atacama Desert of Chile, adjacent to the CLASS experiment and to the Atacama Cosmology Telescope ACT experiment and to the future site of the Simons Observatory. And I'll show you some construction pictures of that experiment. Now, if you could take away the monopole 2.72 Kelvin signal, you'd be left with this fluctuation pattern if you had appropriate contrast. And you could even start to distinguish polarization signals if you happen to have a couple of polarizers nearby, and you could twist and orient them connected to your very high sensitivity detectors. And if you do so, you can decompose the pattern of microwave polarization into an E-mode pattern and a B-mode pattern. And you see here some cartoons from Kamiankowski and Eli Kovet's paper from 2015, Annual Reviews. And you see from the BICEP 2, our artwork there, the kind of types of physics that are responsible for both E-mode polarization, which has been detected since the DAISY experiment in 2002, and B-mode polarization of a primordial type. As I say, we have detected the lensing of the top panel A. We've detected that acquiring a bit of B-mode type character, swirling, twisting, parity, asymmetric polarization. We've detected that that's caused not by primordial forces, but by dark matter operating in the intermediate universe, say peaking at a redshift of 1 or 2, or maybe slightly higher, but certainly not primordial at redshifts of thousands or millions even, as we could hope to probe with the CMB B-mode polarization at large angular scales. And that's where a lot of the interest lies in the constraints on inflation that a B-mode mission, CMB stage 4, Simons Observatory, Simons Array, et cetera, could provide. In 2014, as I mentioned, we announced the discovery of a signal. Now, this signal on the lower panel, the B-mode signal, this is from updated data. I'll say more about that in just a second. You see the phenomenal level of precision that we're getting to. We're getting to 300 nanokelvin level polarization, or 100 nanokelvin level signals in polarization. And I remind you, your eye is actually slightly polarization sensitive. The macula has a pigment which is slightly polarized, but there's very few humans that I'm aware of can detect the polarization of even the atmosphere, which is actually highly polarized compared to the CMB's B-mode polarization at parts per billion. Remember, this is a fraction of 2.7 Kelvin. We're hoping to get down to the parts per billion, few parts per billion of that signal. Just phenomenal. You could not have predicted it. If you told Penzias and Wilson, different Wilson than the Wilson that you guys are affiliated with. But if you told Penzias and Wilson in 1965, Gordon Moore is going to come along in 4 years and come up with an eponymous law, Moore's law, and the CMB detectors will double every 2 years or maybe even every year in their sensitivity, they would not have expected that you could detect levels of signal that we are routinely detecting with the instruments observing today after 56 years elapsed time. It's just astounding. Now, of course, this made a huge headline. We announced it as ripples from the Big Bang, et cetera. And we all, so as I say, some of us more than others, this is on CNN and others. If I was giving a talk on inflation, I'd keep going on this theme, but I want to get to the other topics today. But I will point out that we do have a constraint paper, the BICEP team rather, has a constraint paper that's coming out very soon, the abstract for which is on the web. And PRL, it's been accepted back in August, and it should come out in the next few days. So the constraint is extremely, exquisitely tight. It's 3% tensor to scalar ratio. And again, I'm not going to get into that. I could come when I come and visit for some deep dish, Diet Coke and gum. I will certainly be happy to talk about all the progress we've made in this field. Hopefully even more so when the BICEP array, the successor to BICEP Keck, comes online, as well as the Simons Observatory and Simons Array instruments. Of course, we know what happened in my book. I explain in excruciating detail what happened with the original announcement in 2012. Now you notice this is an upper limit at 2 sigma upper limit effectively of less than 3.6%. And that's exquisitely constraining and something I never thought would be possible when I proposed to build BICEP back in 2001, exactly 20 years ago today. And it's just astounding because the progress is come at great cost, literally, figuratively, et cetera. And it's just amazing that this team has done spectacularly well at constraining inflationary models. But of course, there is no one inflationary model. You give a theorist enough coffee and they can come up with as many as you like. But in the context of the types of models I'm going to be talking about in just a minute, there are sort of asymmetries that can be detected that in some sense are even more interesting than the inflationary signals that we kind of all expect, right? I mean, we would be very surprised. And in fact, almost all the alternatives to inflation that I mentioned, namely the conformal cyclic model of Sir Roger Penrose or Paul Steinhardt and Aegis's bouncing models, or Robert Brandenberger, Kamran Vafa's string gas cosmology, they all feature some vestiges, I would say, of an inflationary model where they have scalar fields. They actually have inflation built into them, say, or they have to predict things that we don't believe in having evidence for, at least at this moment, like error bonds, et cetera, et cetera. So there are difficulties with all the alternatives as well, don't get me wrong. But if we discover either one of those 4 different alternatives is correct to inflation, they aren't as dissimilar to inflation as one would naively think by hearing the word alternatives. So it's quite expected that inflation is at least correct for some version of it for providing seeds of cosmic structure. And I think that's the most successful way to think about it, not think about it as a seed of cosmogenesis. I think that's incorrect. But what I want to talk about now is not the death knell, what happened afterwards when we discovered that our signal was attributable to dust, and that was done in concert with the Planck team. I'm not going to talk much more about inflation, except to say that we are chastened and hardened by these results. And we now know that one must, as we did know back then, I shouldn't say it as if it's a new found discovery, that we have to look for all systematic effects, even those that are astrophysical but not cosmological, such as dust. And so we build into our instruments, as I'll discuss in a bit, we'll build in the capability to measure cosmic dust as well. Keating, that great experimentalist, Mahatma Gandhi, nominated the same number of times for the Nobel Prize as Adolf Hitler, never won it though, neither one of them won it. He said the seeker after truth should be humbler than the dust. The world crushes the dust under its feet, but only the seeker after truth should so humble himself that even the dust could crush him. Only then, and not until then, will he have a glimpse of truth. So we have to be humble when we approach the cosmos, and that includes building in the capabilities to measure cosmic dust as well. And it will turn out that dust is much, much less pernicious in searches for these moving violations that I'm about to discuss. So let's talk about birefringence first. What is birefringence? It means double refraction. It was first observed in the 1600s, and this effect is illustrated by a piece of Icelandic spar calcite, which shows 2 different images because the ink, say, that's producing the words calcite and the line, those are propagating through an asymmetric crystal that's not amorphous, it's not like glass, and it's not a crystal that has cubic structure either. It has this orthorhombic structure, which then gives it 2 different indices of refraction. So horizontal and vertical light propagate at different speeds, as if there's 2 different indices, like your glasses with such a material would look quite confusing to you. Life would look even more confusing than it already does. And you can suppress one of those with a polarizer, and I have a video coming up about that. But the phenomenon was not really understood until Fresnel, famous Fresnel and Robert Young, and the wave theory of light. It did give a lot of credibility to the wave theory of light, and actually is only interpretable as a byproduct of light, of the electromagnetic radiation that we call light, having a transverse character. And that was one of the first instantiations of that. So I think it's very cool. This goes back 400 years almost, this phenomenon. And yet now we're planning to look for it not in our chunks of rocks found in Iceland, but in the universe at large. And it has an even cuter connection to the projects that I work on. Here's kind of a distillation of this from Greg Gabadadze. He's a friend and associate director of physical sciences at Simons Foundation. And you see in the lower right, that's Jim Simons talking about what is a Chern-Simons 3-form. It's the same Chern-Simons, the same Simons rather. SS Chern, sadly, is no longer with us. But they worked out a purely topological invariant that is a 3-form. And it's unlike almost any other kind of mechanism in physics, but this can actually endow, in a way that I'll describe, can endow light potentially with a type of birefringent character that could be detected only on the largest cosmic scales. And I think it's just fascinating. And again, it tickles me that it's the same Jim Simons as is responsible for supporting almost 90% of the cost of the Simons Observatory and the Simons Array. So it's quite astounding. This man, Jim Simons, has had wonderful careers and contributions in 3 different fields at the highest levels, from mathematics, where he was chair at Stony Brook for many years, philanthropy, and obviously in the hedge fund world. So this type of 3-form, when the proper derivatives can be obtained, you see there's a preferred 3-vector component of p mu, which then can break Lorenz invariance symmetry. And then manifestly, it will also break parity symmetry in a way I'll describe. So what would Lorenz invariance violation mean? It would mean many of us would either be fully employed or unemployed, because it would mean that the standard model is based on sort of a shaky foundation that I'll analogize in just a second. But the built into both GR and the standard model of particle physics is Lorenz symmetry. Invariance under boost, no preferred reference frames. I like to say the universe doesn't care about where you are, who you are, what you are. The laws of physics, according to Lorenz, are symmetric. And yet, if we believe that eventually we could unify GR with quantum field theory, i.e. make it part of the standard model, as is the holy grail for folks ranging from Einstein to Frank Wilczek and Juan Maldacena and many other people that have honored me on the show. Nevertheless, I think it's quite fascinating that if you violate Lorenz symmetry in a convincing way, it could point us in a way to new insights, at least, into quantum gravity. So this slide from my friend at Cal Poly San Luis Obispo, Matt Muse. And he makes this little cartoon that shows everything in physics that we teach to our undergraduates built on these bricks and these blocks that my kids like to knock down. But the three pillars are quantum mechanics, the curved space-time of GR, and Lorenz symmetry. And if there is a theory of everything, of course, there's no guarantee there is a theory of everything. But if there is, would there not be a shift, an observable shift downstream if Lorenz symmetry was not an exact symmetry, as we assume it to be? And it's not so crazy to think about that, because we know that there are symmetries once held to be sacrosanct, such as parity and charge invariance, discrete symmetries that are known to be broken in not only in the standard model, but also in things ranging as diverse from the origin of life and prebiotic chemistry, as I say, to our own bodies, et cetera. So parity invariance is broken, and it is a well-known fact of nature, predicted, as I'll show here, in the 1950s, theoretically predicted. And this is really astounding, because I think this led to, as you guys are much more expert than I, those of you who traffic in particle accelerators, that these decays were found to be quite asymmetric under certain types of discrete symmetry invariances. And that was then thought that these parity violations were held to be true. The invariance, rather, was held to be a component of the then standard model in the 50s. And it was sort of theoretically predicted based on data from these experiments that were built in instruments like Brookhaven and other places. And I think it's quite fascinating, because very soon after this paper, the question of parity conservation, was published in a Physical Review. Only about a few months later was this actually tested, and it was tested at Columbia, at the laboratory in Columbia, and also the National Bureau of Standards, now called NIST, by Chien-Hsun Wu, Madam Wu. And this was done, she did it over Christmas, 1956. And then they submitted the paper 2 weeks later. It's really an astounding thing. And I asked my friends and followers on Twitter, what's the most important experiment ever done? And many people put up this experiment, the famous Madam Wu experiment, that have revealed that cobalt nuclei, as viewed in a mirror, exhibited this anisotropic emission just the same way as if you reverse the direction of spin. And that shouldn't hold true if parity was maintained, if CP was maintained. And this involved an incredible tour de force of experimental technology back in the 1950s. I mean, we have dilution refrigerators, et cetera, here as part of the Simons Observatory, and we bought them, and they only get us to 6 millikelvin. And to get down to 3 millikelvin and do this and observe also this as a particle experiment and do so, over 60 years ago, it's just astounding. And do this in weeks, a month, just a few weeks after the paper, and submit it and have it detected, obviously, with such high confidence. And it was confirmed months later by Letterman and others. You can probably, and I do have another video about that coming soon as well. Unfortunately, this did win Nobel Prizes for Lee and Yang, who's just celebrated his 99th birthday, I believe, yesterday. And so they won Nobel Prizes, and that was nice. But Madame Wu, she just got a stamp, and that's unfortunate. This year she was honored with a forever stamp. I mean, it's good that she got a stamp, but many think she deserved her share of the Nobel Prize. So how could you measure CP violation? You can do so using what we call cosmic polarization rotation, CPR. And you see this picture from moving violation that I once got, but you see the initials on the police cars in New York City there, CPR. I think that's pretty cool. So what could you do with a violation like this? Well, Sean Carroll in 1990 and Roman Jakiv and George Field, they wrote a POCL paper, which is still cited many hundreds of times a year. And this paper really worked through as a worked example what would happen if you added to the Maxwell Lagrangian, if you added this three form, this four momentum, the P mu that I said before, now it's PA, coupled to the electromagnetic potential and the Maxwell tensor. And if you couple those together and just go through and grind out Maxwell's equations from those, and then you substitute in and obtain the wave equation, you'll find there's a dispersive wave equation. And the wave equation is dispersive in that it has a slight preference for left circular polarization versus right. And Sean and others explained that in 1990. And this has the net effect of rotating the plane of linear polarization after traversing some distance through the universe, exactly as light passing through a crystal, calcite crystal, rotates the plane of polarization as well. And in fact, you can suppress one of the two polarization states with a piece of linear polarizing material. And the effect is illustrated here as I show. Starting on the left, you have the electromagnetic field polarization vector classified by the electric field direction that determines the polarization state, starts off purely vertically, traverses some distance of optically active calcite, and emerges rotated by 45 degrees. And it'll rotate more if the calcite is longer, and if the birefringent term, the optical activity, is larger. And it's actually very, very slight. So you need decent thicknesses unless you have materials like calcite and crystalline quartz. And we actually use that property of materials, especially sapphire and synthetic sapphire, aluminum oxide. And we don't use calcite for microwave telescopes, but you could, and it would rotate the plane of polarization. We use that to create half wave plate polarization modulators, because you only want to modulate the signal that you're interested in detecting because it's very faint and the background is unpolarized largely, even though it's a billion times brighter, it can remain unmodulated, and you lock in phase sensitive Dicke switching on the polarization signal. And so you can rotate this block of orange material here, and you rotate that at some rate, and the polarization will rotate at twice that rate, because polarization has this unidirectional spin one character. So you look for a preferred direction in space-time, and I always joke that, that this has actually been found already. It was predicted in the cosmological context by your friend not too far from where you guys are, Mike Turner, and his student Widrow, I believe, and that was 1988. They wrote down this, again, whenever you see Maxwell type tensor with itself contracted on with itself times a four vector like GA, or the three components of a four vector, that you can actually expect some kind of optical activity. And the amount of rotation beta will be the path length, which for photons is just the time of observation subtracted from the time of emission times the speed of light. And you'll get a rotation, this phi dot, theta dot, and you can go through the math yourself. It's actually a really exquisite paper. And this was claimed to be detected multiple times in cosmology. And so here's the original paper I showed you that where Sean and George and Roman worked through this, and they come out with this Chern-Simons. I like to point out that it was published on February 15th, which all of us Galileo aficionados know it was his birthday, Galileo's birthday. And then they go through the math and they come up with the electromagnetic contribution, the Chern-Simons term, and that kind of rotation. And they talk about ways that you could discover it in topological masses, gauge fields, et cetera. But this is the first application to cosmology and astronomy. So recently, as I said in the abstract, there was a claim detection of this effect or evidence or a hint for it, or the tentative. There are a lot of provisos, okay? So my friend Ichiro Komatsu and Yuto Miyanmi, who's a collaborator on Polar Bear, which I also am affiliated with, they claimed hints of the nature potentially of dark energy, because a preferred direction, purely one in time, would result in an isotropic rotation of polarization, all about the same axis, all in the same preferred handedness. And the amount of optical activity, the amount of rotation, would be proportional to the optical path length, and that's proportional to the time of emission, as I said, subtracted from the time of observation. And so Miyanmi and others say that this could actually be related to quintessence. Quintessence being a derivative in some sense of the dark energy, of dark energy's properties over cosmic time. And this would sort of sample that dark energy evolution at different times from the earliest time to today. And actually you could see it and sample it versus redshift in some work that I've done with collaborators using quasar polarization. You might be able to get actual samples of the derivative of this term, and that's a talk for another day. But it'll be interesting because we all assume that that perhaps dark energy is a cosmological constant, but how do we know? Again, this would provide a breakage of Lorenz invariance symmetry, if you like, with respect to time. It would say there really is some sort of preferred frame, and maybe we're in it right now. Some find that very unlikely. And so this got a lot of attention. It kind of reminded me a little bit of the Bicep 2 result. And so this is the thing I talk about. They use the Planck satellite data, and they go through this. This characterization, citing Sean Carroll and Turner and Woodrow's paper, and they come up with a plausible, sort of hints below 3 sigma by far, but still interesting and perhaps probative. But as I said, I believe that this type of phenomena is almost time translation invariant, in the sense that it seems to come up every decade or two that people discover a detection of this effect. And you see here another, this is from 1997. You see here some people that are still in the news today. There's like Newt Gingrich, you still hear about him. You hear about Benjamin Netanyahu, there he is on the left. But like that, you find out an interesting headline in the lower right, and it says, "This side up may apply to the universe after all." And this was a claimed detection from radio galaxies at intermediate redshift, that they had a preferred polarization property distribution. That polarization effectively was birefringent. There was an what's called an ordinary axis, as in the crystal of calcite, and an extraordinary axis. So radio waves coming at different angles from different polarized sources in the intermediate redshift universe would actually cause different amounts of radiation to be polarized, depending on how far they've come from and depending on what polarization you're measuring. So they go through here, and I love another one, actually another quote that's time translation invariant from our friend Jim Peebles in the lower left. He says, "It would really be a profound change in physics if it is true." And you hear that a lot. Actually, I heard that from Ichiro Komatsu, quoting Jim Peebles in the announcement made in 2020. So you're talking about, 23 years after this paper was written. And actually, this result was only unsubstantiated, disconfirmed due to an analysis by Sean Carroll, who you would think would have wanted this effect to be true more than any other person. And yet he found they had made a huge statistical error in the analysis, basically a real blunder in this case. It wasn't like a systematic error. They misinterpreted the way that radio polarizations are reported. And so it was, they didn't recognize that a 0-degree polarization angle is the same to an astronomer as a 180-degree polarization state. And they would count those differently. And then when you added up 0 and 180, or minus 180 and plus 180, you would get the same. You get a result which, when average, would go to 90 degrees, which is what they're showing in that upper right plot. That things at right angles to each other were producing similar types of behaviors, which would be forbidden if the standard model was perfectly Lorenz symmetric. But anyway, so this is saying that the universe has a birefringent property to it. And then about 10 years after that, 2009, or so, we had another paper that came out that said probing CPT violation, basically claiming a 3+ sigma detection of CPT violation and concomitant Lorenz invariance. You see the Chern-Simons term at the top of the abstract, using bicep data and quad data. And this we later invalidated primarily through the propagation of errors, where they basically treated all these experiments separately as if they were completely independently, even though many of them were measuring the exact same signals. And fundamentally, we have built-in calibration uncertainties that really wreck the precision, wreck the accuracy of these results. And so you can get very high precision, but the accuracy is compromised in a way that I'll explain, and I hope that we'll improve upon. So what did the 2020 results say? Again, it showed a basically 2.4 sigma level exclusion of birefringence, which is equivalent to 99.2%. It always sounds better in percent than in sigma. And, as my late great colleague Hans Parr said, at 3 sigma, they'll invite you to give a seminar via Zoom. But at 5 sigma, they invite you to Sweden. And so it's not really key, if we should really be paying too much attention to a 2.4 sigma result. And nevertheless, I think it shows and portrays, rightly so, the interest that we have in probing Lorenz invariance, et cetera, with telescopes like this. So here's a compilation that one of my students made a couple of years ago, and I added on the Miami and Komatsu results. So these are all the CMB experiments in red or radio and ultraviolet measurements. Ignore those, but almost all the CMB experiments were consistent with a less than 0 cosmic polarization rotation. And as I say, the game-changing nature could only occur if the result can be confirmed. And so far, we are still working on this. So I already talked about E modes and B modes. For these signals, we look for so-called forbidden correlations, correlations that should not exist unless there is a tiny, and it has to be tiny. We know from solar system probes that this effect can't be very big. We know from CMB observations that this result must be at sort of the sub-degree of rotation. It's a few arc minutes at most. And yet we believe that will be eminently measurable by upcoming instruments like Simons Array and like the Simons Observatory that I'll talk about. So the Simons Observatory was funded about 5 years ago. We're almost done with construction of the project. It comprises 4 telescopes, 3 small aperture telescopes designed to go after primordial B modes. Here's the site. This is a different view as before, looking now to the southwest. And it shows the Atacama Cosmology telescope class and the Simons Array in the foreground. We did a groundbreaking 2 years ago with Jim and Marilyn Simons. They're on the right. So I put the 26th richest person in the world to work, shoveling dirt at 17,000 feet. I can add that to my CV. There's Adrian Lee on the left and the current president of the Simons Foundation, David Spergel, in orange. Marilyn and Jim have finally retired from those positions, but they're still hard at work as always. So our main targets for the CMB projects on Simons Observatory are to measure primordial B modes, lensing, clusters, E modes, et cetera, et cetera. But I want to talk about, here's a collaboration at our last face-to-face meeting. We hope we'll have one here in San Diego next in July of 2022, finally. It's been too long. And so it's a huge team, about 300 scientists, 45 institutions, every continent on the planet, including Antarctica. And this is a fascinating instrument that, here's the location here, that we have to build from scratch. There's no support here. We have to truck up our own concrete, our own diesel fuel. Here's some concrete being poured for one of the platforms for the small telescopes. This is back in March. So we're finally getting over COVID, and Chile's done quite well, but still there's shutdowns. But we have to do everything ourselves. This is at 17,200 feet above sea level, 5,200 meters. What are we building? As I said, a huge telescope, a 6-meter diameter, large aperture telescope, and 3 small aperture telescopes, one of which is in the high bay directly across from my window here at UC San Diego. And we'll have 6 frequencies as shown here, and that's to mitigate against dust and synchrotron radiation masquerading as primordial B mode polarization. They're enclosed, these huge telescopes, are not huge, these are actually small. They're about 50% bigger than the original Bicep 2 instrument and aperture, and but they're refracting telescopes, just like Galileo and just like Bicep 2. These are very simple instruments, the cleanest optical system you can possibly implement. Then they have to be surrounded by these large ground screens, And then there's a large telescope, which is the biggest CMB instrument ever devised physically. It's 2.3 meters in diameter. So you can have 5 graduate students, kind of arranged inside at a time, and comfortably not violating COVID restrictions. And these are cooled to about 0.1 Kelvin using dilution refrigerator, DR gas system using helium-3, helium-4. And we install these, and here's just the ones at UCSD, the only ones I can take pictures of. So here we are with the telescope. That's an actual telescope. The white object is the cryostat. It gets its detectors made by Suzanne Staggs' team at Princeton and NIST and SLAC, and then we integrate them all together. And the detectors are phenomenal. And I would encourage you to have Suzanne speak about how these wonderful detectors of hers work, really the beating heart of these instruments. And we believe that they'll be both the most sensitive individual detectors, but also the most sensitive arrays of instruments. These are going to be deployed, as I say, starting in early 2023. We believe we will get first science observations, including probes of CMB polarization violation, Lorenz invariance violation. And then we'll be observing with the large telescope. Again, Mark Devlin is leading that. You should invite him to give a talk about the LAT science, which is so fascinating. But what is the bugaboo? It's systematic errors. How do we get rid of systematic errors? Well, the best hope for getting rid of systematic errors is actually to build our own calibration sources, because there are no actual, I'm going to skip over this, but if you miscalibrate your detector by some rotated amount that you're ignorant of, you will get a B mode, exactly 100% conversion of E modes, which we know exist for 2 decades now, and it'll rotate completely into a B mode, and it'll produce 100% correlation of the forbidden variety that is indicative of these Lorenz invariance violations. So we have to be very careful about that. And so these signals get quite hard to get rid of. And actually, it's much harder to calibrate a signal for measuring this birefringence signal than even calibrating for the inflationary B mode signal, because BB goes as the systematic error term omega squared, whereas, say, the TB term that we would look for as a probe of the evidence for Lorenz invariance violating signal only goes linearly with this small, and these are small numbers. So omega squared is completely negligible, but omega is not. And so we have to be careful about that. And so one of our colleagues, Rolando Dunner, is a physics professor at Pontifical University in Chile. He's gotten funded for a drone. I promised you drones, and I don't want to let you down. So he's built this drone system and has now gotten a very large, he's got 250 million Chilean pesos, but that's a lot of money. It's still a lot of money. And he can actually do better by far than the Planck satellite, which was responsible for providing the limits that have become so provocative in this field. And he sent me a video. This is the site. So he does very precise photogrammetry of our site, and he tests it out. And he's going to be building a source, because there are no natural sources of 100% understood microwave polarization. And that's what you need to calibrate to make an accurate measurement. So, so here he is flying his drone. I think it'd be cool to deliver, some biscotcha sandwiches. These are these little rodents that live up there. But anyway, this is a phenomenal instrument that he's building with his team. And here's one of his students and one of our colleagues calibrating it. Here's the flying over the system. And so it's from this vantage point, he can park and station keep and spray 100% known polarization signals into that telescope. That's the Atacama Cosmology telescope. And then that can be scanned. You see the telescope moving, and again, an extremely accurate calibration of your signals. And that's what's needed to get below and confirm or refute the results of Mianmi and Komatsu. So what's next? I'm going to conclude. This is a very fascinating subject. This is just as of a couple of years ago when my undergraduates plotted how many papers reference this effect: Chern-Simons, cosmic birefringence, Lorenz invariance. So it started with Sean Carroll's paper I showed you before, just one reference in 1990, and now there's hundreds per year. This stopped in 2014. And it could reveal, as we show here, the presence of what's known as a crisis. So Steve Weinberg, late great Stephen Weinberg, said that physics was short on crises, even though we thrive on crises. But today it's full of it. And we have a lot. As Mike Turner often says, precision cosmology is great, but accurate cosmology is even better. So we need to do better with respect to systematics. It could be astrophysical systematics. It could be instrumental systematics. Can we solve concomitantly? We can measure primordial magnetic fields. the earliest magnetic fields in the universe with the Simons Observatory. We have papers about that. Is a CB, cosmic birefringence, hint real? Is dark energy constant? Is it like quintessence? What is dark matter made of? Another allied concomitant thing we get for free is constraints on axion-like particles via their shift in the CMB's polarization that we detect, and we measure it daily with a sensitive instrument. We can actually test for axion electromagnetic potential variation. And then, is Lorenz invariance a sacrosanct aspect of physics? And there you see Dan down there talking about the implications for G-2 back on my channel. So again, I implore you, shameless plug, didn't write the book to get rich, but 99 cents, I think most of you guys can afford. And it's only that cheap for this week. So please do me the honor of that. Better than winning a Nobel Prize for sure, distilling their knowledge and their wisdom into life hacks for STEM professionals like ourselves. And lastly, yes, please do subscribe to my YouTube channel so you can take a picture. And now I will take questions. Sorry, I went a little over you.
Rory, thanks a lot. Yeah, thank you very much for the talk. Let's give Brian a round of applause. Thank you very much. And please raise your hand or directly unmute yourself to ask a question. Let me make sure I see all the views sign together. Okay. Yep. Is there any question? Oh. Yeah, maybe I'll ask the question first. So among all of these kind of new anomalies, or as you say, like the crisis, which one do you think is the most promising for us to understand the universe better?
Well, I think there are a lot, and there's no shortage of them. We think it could be that there could be both contributions from early dark energy, say for the Hubble constant tension that's come to the fore recently, both from potentially the contribution of early dark energy, maybe being different than late dark energy, or it could be the injection, and that's an unknown signal, but we know for sure that magnetic fields exist in the universe, and they could have played a much more prominent role, as Colburn Turner pointed out in 1990 in the famous book. The injection of magnetic field stress energy will produce a change in the Einstein perturbation equations, and those will produce B modes that could be effectively downstream, can be measured by only sensitive, precise, and accurate instruments. And that could do two things. First of all, it'd be great to have a measurement of the earliest magnetic field in the universe in a structure that's not gravitationally collapsed as is currently measured. And there's actually a lower limit on the amount of magnetic field energy, and that comes from Gamma Ray Observatory. But that limit is that the magnetic field, the primordial magnetic field string, has to be greater than 1 micro nanogauss, which is not great. But seeing as the current upper limits, so we have a lower limit and we have an upper limit from CMB experiments that's about a nanogauss. Closing that huge 16 order magnitude, 15 order magnitude gap is not going to be easy, but perhaps our only hope is to use the CMB. And then we know that magnetic fields exist, so they must have started with the very first one, right? There must have been a chicken or egg. There must have been an egg at some point, even if the chicken came first. So it'd be very interesting to me to measure. I like to measure signals that are known to exist, and having a lower limit, as was done with neutrino oscillations, to get lower limits on mass. That's another thing we're looking for. So I think the most likely solution could be primordial magnetic fields, just with a Bayesian prior that we know magnetic fields exist, but none of these other things do we know exist.
I see. Thanks.
Hey, Brian, can you give me an idea of what people have in mind for the origin of these magnetic fields? Like, I know people talk about topological defects and phase transitions leading to them, but like, I don't think those will lead to the kind of magnetic fields you're talking about. Can you give me an inkling of what might be behind something like this if you were to observe it?
Yeah, this is, it's definitely more your bailiwick than mine, but I have heard in the context of certain inflationary models, some gut models, that you would have residuals. It may be, it's a very delicate interplay when you make magnetic monopoles and when you get rid of these magnetic monopoles and gut theories, we obviously wouldn't observe any in our universe if inflation took place, our observable universe. And nevertheless, I think there are, expectations that at some level they must be nucleated, and there might be, as I say, magnetic monopoles or domain walls or some other allied physics, cosmic strings, things like that, that aren't completely outlandish as the source of magnetic fields. Again, it's like, where did neutrinos come from? It's not necessarily something I'm going to engage in speculation about, what caused the origin of these things, or inflation itself even, but the downstream effects that to have a Milky Way sized magnetic field, of order, tens of microgauss, you need to start, there's just not enough time for magnetic dynamo activity to take place, or clustered dynamo activity to take place. So you have to ask, well, was there some seed to generate the observed levels of magnetic fields that we see in collapsed structures? So answer your question, there are some, theories for this. Kolb and Turner discuss some primogenitors for these magnetic fields, but yeah, I wouldn't say that any of them are on really strong footage, except, and for an observer's perspective, they just have to exist for us to measure them, and they have to be above the threshold of our detectability.
Thanks, Brian.
Yeah.
Thank you very much. I think we have a last few minutes. If there's some question, feel free to ask right now. And take a look. Okay, I think that's all the questions. Yeah, thanks a lot for giving the talk. And let's give Brian. Oh, actually, is there a question? Oh, actually, yeah. I think there's no question for now. Yeah, and let's thank Brian again. Thank you very much. And yeah, we're very happy to have you. And thanks everyone for coming to the talk. Yeah, thanks a lot.
Thanks, guys. It was great, Yudai. Take care. I look forward to seeing you here.
Yeah, thank you very much.
Okay. Bye-bye.